Okay, I guess we can start, right? So thank you everyone for coming here. Our speaker today is Elena Hartford, who is our own mechanical engineering department graduate, I think in 2015.
Yes.
And after that, she worked as mechanical engineer for several years, designed HVAC systems for residential and commercial buildings, and now she's in sales. So I'm looking really forward to hearing from Elena.
Thank you. So I'm here today to talk about VRF technology, and just keep in mind that I do work in sales, so everything's going to say LG on it, but I'm trying to talk about things more in general today, not sell you a specific product. So I'm going to talk about various manufacturers, even though everything is going to say LG. So let's get started. So today we're going to talk about the definition of VRF, a little bit about the history and the market, and then some about fundamentals, because that's the important stuff that all the engineers like to know about, and then some benefits, why you should be using this technology or could be using it, or how it could help your projects, and then also some design considerations, because we do live in a cold climate. So the definition, ASHRAE definition, you can all take a minute to read it, or I'll read it aloud. So variable refrigerant flow or variable refrigerant volume, that's Daikin's term for it, the VRV system, is an engineered direct expansion multi-split system that incorporates at least one variable speed compressor distributing refrigerant through a piping network to multiple indoor fan coil units, each capable of individual zone temperature control through integral zone temperature control devices and a common communications network. So don't try to memorize that. We're going to talk about it later, but just keep some of those terms in mind as we go on. So history and development. I'm going to go over this a little bit quickly because I know we don't have tons of time today, and if anyone is interested in more details, I can send you PDFs of this information. So basically, VRF started in Asia, so you see major manufacturers in Japan, recognizable names like Daikin, Mitsubishi, Fujitsu, Hitachi, really recognizable names. South Korea, we have LG and Samsung. And in China, we have fewer, less known names. And then we also have some manufacturers in India. So just keep this in mind that the major manufacturers are all in Asia as we go through this. It's because while everybody is racing to improve cooling, the United States went with chillers and Asia went with VRF. So we worked on improving VFDs on pumps, that sort of thing, to make cooling more effective. Asia said, no, VRF is the way to go. Let's use refrigerant instead of chilled water. So VRF is an older technology than a lot of people here realize. It was actually invented back in the 1980s. And through the 80s, a lot of those main companies I showed you on that first page were developing their own styles and their own forms of VRF. And then in the 90s, they continued development, making it better until the 2000s when they decided it was useful, stable technology. They'd been using it in Asia for a long time, and they started to bring it to the US markets. Various companies came over at different times. And then in the later 2000s is when they started to decide that making mergers and having joint ventures and acquiring American companies was actually a better way to get the technology over here. So that's why you see things like Trane name branding Samsung, and then eventually switching to pairing with Ingersoll Rand and Mitsubishi is now a partnership in the later 2000s, as of a couple years ago. And so that's how they started bringing their technology over, by making these joint ventures and acquiring American companies. So brief history, like I said, I can send it to you if you're interested in reading all of the details yourself. Moving on to a brief look at the market. Again, I can send you this part if you're interested in looking at it at your own pace. So like I said, VRF has been used in Asia since it was invented in the 80s. And that's why you have 25% of commercial buildings in Europe using it and a whopping 35% of commercial buildings in Asia using it, opposed to another type of HVAC system for commercial buildings. On a global scale, you have general increase in the number of systems installed every year. It's about 100,000 systems installed per year of an increase on a yearly basis since about 2012. And I apologize that my data doesn't go to the most recent year of 2019, but it's a little bit old. So general increase in this technology, you can see it's catching on. People do want to use this technology. Similarly, in the United States, we have a $20 billion HVAC market. 5% of that is commercial VRF. I know that sounds kind of small, especially when you look at the whole rest of the graph, but that's $1 billion for VRF, even though it's a really small section. So when you think about that, there's a lot of money going into VRF, and it's something that we just want to keep an eye on because of that. And really quick, I want to say I apologize, the font isn't showing up properly. So I apologize if things look a little wonky up there. That didn't get sorted out in time, I apologize. So then in the US market, we're seeing similar type of growth with more systems being installed every year as this technology starts growing here as well. And I have numbers on the next fancy page. So economists are estimating that there's an 11% annual growth potential for this industry through about 2023 to 2025. That's kind of where they're estimating. They don't go too far out, but 11% growth. So it's definitely something that's up and coming, and we want to stay on top of knowing what's going on with this type of technology. And in terms of vertical markets, you can pretty much use it in any type of application you can imagine: residential, office buildings, churches, gathering places, community centers. Just think of anything and you can kind of do it. Does this work? Does this not work? Once we go into the fundamentals, and you can pretty much find an application almost anywhere. So fundamentals. So we're going to revisit the definition a little bit. Like I said, you didn't have to remember it because we're going to go over it now with the highlights. So it's a direct expansion system, which means refrigerant. So you're going to have refrigerant piping. Then it's a multi-split system, like I said, not like a mini split, so not one-to-one. You have multiple indoor units all on the same, we're going to call it an outdoor unit for this presentation. It can also be a heat pump, but we'll get into that in a minute. And then you have a variable speed compressor, which is in that outdoor unit, this guy. And then it's also individual zone controlled, which is one of the important parts of that definition, is that you have individual zone control, which means you can put a thermostat or controller on any of your indoor units, and you're going to get control for this separately with its individual controller. So not everybody has to be subject to whatever one person in one office with a thermostat wants, like a VAV system, for example. So there are two different types of VRF, and the first type is a heat pump, which allows you to be in a heating mode or a cooling mode. So you could be all heating for all of your indoor units, and you still maintain control of your zone by modulating how much your fan is on or whether the unit is on or off. Like, it can still control your temperature that way, so you're not necessarily going to be overheating or, in the other scenario, overcooling one office, but you're not going to be able to heat one office while you're cooling another office. If you want to do that, we go to the second type, which is heat recovery, and that allows you to do simultaneous heating and cooling so that anybody in a room that has a controller can do whatever they want. They can be in any combination of heating and cooling that could potentially be divided out for whatever reason that your zones might need. So just note that even heat recovery still does operate on the basic or general principles of a heat pump. So even though it allows you to do simultaneous heating and cooling, the principles are still the same. So that's why I'm going to talk about heat pumps first. So we know that a heat pump uses a refrigeration cycle to transfer heat energy somewhere that it really doesn't want to go. For example, you're going to take cold energy from the inside and reject it to the cold outside. If you want to, in this picture, if you want to be cooling, you're going to take hot energy from indoors and force it outdoors, where it's also doesn't really. That's a hard way to transfer energy, but that's what this device does. It inputs electrical energy, and then does a refrigeration cycle and achieves this. And then we have the heating cycle as well if you reverse it. So you can see both. And just notice that your evaporator and your condenser are what switch when you reverse that direction. And we're going to put it on a pH diagram in just a second, right here. And then you can see how that will work. Notice that on your cooling cycle, your condensing happens in your outdoor unit, and your evaporation happens on your indoor unit. Because you're rejecting heat that doesn't need to be inside to outside, and here you're taking that heat out of that room, evaporating gas, and bringing it outside. So then we have the opposite, which you achieve with a reversing valve in one of these systems. It's already in the system. You don't have to worry about trying to add that. It's just in there. And you've switched it now where your indoor fan coils where the condensing is happening and evaporation is happening outside. So just basic refrigeration cycles, but good to keep in mind because these are the fundamentals of how these systems function. So for a minute, let's just think about the efficiency of refrigerant and the space it takes to transfer this heat energy we're talking about using various media. So this here is approximately the size, it's to scale, of a duct that would transfer 20 tons of cooling. It would be 40 inches by 20 inches, which is pretty big, compared to a 3-inch cold water line to transfer the same amount of cooling, or a 1/8 inch refrigerant supply line. So basically, you have a volumetric efficiency savings that is quite huge. And so if you have projects where you need going to take up a lot of space, this is a great thing to consider because you have that efficiency of keeping that refrigeration cycle the only heat transfer cycle. Like you're not trying to transfer heat or cooling to air that doesn't want to accept the energy as readily as refrigerant wants to. So let's just look at this really quick. We have 50 tons of refrigerant piping here. This one's a little harder to see, but it's like going down this, like this is the floor, and it's actually going down that chase. For some perspective, we have 12 tons of refrigerant piping, or 12 tons of ductwork right here, and then this is 40 tons of refrigerant piping. So you just see the difference in the space that this takes up, because we know that refrigerant really wants to transfer energy. And so just keep that in mind. Refrigerant likes to transfer energy, and it's a really efficient way of transferring energy. So traditional 4-pipe system, kind of like we've compared the size. So I want to talk about the efficiency of the cycle itself. So here you have your condenser water loop, your refrigerant cycle, basically same refrigerant cycle that you would have in a heat pump. And then you also have your chilled water loop, which would be the one inside your building if you're going with the chiller system to achieve the same thing you'd be able to achieve with the heat pump in cooling mode. And then if you want heat, you obviously have to have a boiler too and input gas. So comparing that to, like I said, the heat pump version where you have one cycle and then you can run it in reverse, the same system, and you get exactly the same pieces of equipment, but giving you a whole nother operating mode. So again, space savings and then energy savings because you're not transferring your energy so many times to make it go to the same location, which is inside your building or your conditioned space. So now we're going to talk a little bit about what the different options are for heat pumps. You have air source units and water source units. The air source units are going to use ambient air to relieve that energy that you want to expel, and then the water source ones are going to use a heat sink or a heat source, which is going to be water that you provide, and there's some various methods which I have coming up. And notice that your air source units are going to be mounted outside in various locations, and then your water source ones will be mounted inside. So there are advantages and disadvantages to both. The air source ones are the ones we mostly talk about in this presentation because you have the most potential to make them efficient, and then you're not taking up space inside your building. We all know that nobody likes to take up space that is in some way useful inside their building. But there are applications where they can take advantage of things that the air source system wouldn't, and I'll talk about those in a minute. here's how they would be installed in a rooftop scenario or in a mechanical room scenario. And then here is what the units look like just by themselves, so you can kind of get an idea of the appearance, I guess. And these units are not actually that large. I've stood in front of these, and I'm not a very large person, and I can actually reach out and say, like, this is how big it is. So lots of space-saving potential there. And then in terms of your temperature limits, the air source units can go all the way down to negative 23 degrees now. Both Daikin and LG have developed this technology where they can do that. Some of the other manufacturers are not quite as developed, so their technology does not allow the units to operate in such low ambient conditions. But keep in mind that that is possible. Like, you can still be in heating mode if it's negative 22 or negative 23 degrees out. It's like 22 point something, so I just went safe and put 22. And then it can operate in cooling mode all the way up to 122. So if you're doing a project, not in Alaska most likely, like Arizona or somewhere where it does get very warm, you would be able to still achieve that. And then same with the water source units. This would be the temperature range of your heat source or heat sink that you'd be able to have. So now, like I said, talk a little bit about how you can use the water source units. One option is using a cooling tower. Obviously, that's not your most efficient option, but if you have existing infrastructure, or if you really just want to add on a small part of a system to an existing system and you think building it out with heat pumps makes it more efficient just for that part of the building, there's various energy studies you can do to see if that would be a viable option. Another option is geothermal, and that one's actually pretty cool in Alaska, I think, because you have to keep the ground frozen anyways, so why not take the heat you're leaching into the ground and put it back into your building? So that's pretty cool. There's some potential for that there. And this last one, we have to be a little careful with because nowadays there's regulations that don't allow you to change the temperature of waters out in the general environment because it can affect ecosystems, and we know that now, so we don't recommend that. But in certain places, there are things you could do. I think there's one in California where they change the temperature of the seawater, and then they figure out what level of the sea they can put it back in so that it will match the temperature where they're putting it back. So there are options. Those are just more difficult options, but just so you know, it's something out there. Here's some kind of examples of how you would pipe that. This is the typical, like, I'm just going to attach it to a chiller boiler is an option. People do it. Again, it's the most efficient thing, but there are cases where it still can make an impact and save you energy and money on, even on installation, surprisingly. But again, not the best if we're going for that whole super efficient system. Here's one where you would be just geothermal, which again, they're great places where you can apply that. And then of course you can do mixed systems, any combination, where you're getting what you need out of various areas of the building. Like this one would be good if you were trying to keep the ground frozen, the permafrost frozen, but you also want to have, because obviously keeping the permafrost frozen doesn't really help you get the cooling, because then you'd be heating the ground and that would counteract everything you tried to do to keep it frozen. So beware of those little things like that. Okay, so moving on to kind of how we go about constructing these systems or putting them together. You have various outdoor units, and sometimes we even call the indoor water source units outdoor units just because we don't really have a great name for them since they're not technically heat pumps if you're doing heat recovery. So we just going to call them outdoor units for the remainder of this presentation. If you come up with anything great you want to call them, basically just call them whatever you want as long as it's clear what you're talking about. So these are modular and scalable because you have one unit like so that you can mount on dual or triple chassis and make into a larger unit as shown here. Same with the water source to get larger ton units, and then you can use as many of these really as you need, or even you can use just 5 separate ones if you don't want to string them together. So you can kind of get whatever you need out of the equipment that you have, and this is for across the board from the manufacturers. Like the tonnage might not be exactly equal, but this technology is modular like this. And then when you do have these combined systems, note that the controls are integrated such that they're going to operate as one unit, and you don't have to worry about any kind of complicated like sequence of operation to try to say like, oh, like lead lag this one. Like you don't have to worry about that. It's going to take care of itself within the controls it comes with. And then these would be an example of some of the indoor units. Again, various capacities, various styles. You can mix and match and place these where you need to so that your rooms have what they need and in any combination. Like there's no rules for what type you can use together or anything, just whatever you think would fit the situation the best and has the capacity that fits what your loads recommend. The one thing you do have to pay attention to, though, is your combination ratio or connected load. And that's going to be the ratio of the nominal capacity of all of your indoor units combined divided by the nominal capacity of the outdoor unit they're connected to. So 50% is the minimum required connection ratio that you can have, or combination ratio, excuse me, that you can have in order to even say run on this system. If you have less than that and you try to start it up, you're not going to have the right pressures for the system and with the refrigerant to actually run the system, and it's not going to work very well at all, and it might not even start up. So be aware of that. Don't think, oh, I'm going to build this out later and put like one small 2-ton unit on a 20-ton outdoor unit. It's like, it's not quite like chilled water, and refrigerant needs to be kept happy and within certain pressures and levels that it is comfortable operating in. So then 80% would be the minimum recommended. So if you did want to leave a little extra space for the future, or if someone said, actually, I'm still a little bit hot and they want to have some extra capacity added, whatever you might think the case is, then 80% would be the minimum that you'd want to leave as a little buffer. You ideally want to shoot for 100%. You want your unit 100% loaded. That's where it's going to be the happiest, with the refrigerant level being completely charged with what the system is designed for. So that would be the number that you'd want to keep in mind, and it's the one I keep in mind when I help my customers and clients figure out what they're trying to do with their system. Is I always shoot for 100 unless some other information comes up. For example, you can have 130%, your maximum recommended connected load or combination ratio, because you might have some diversity. We all know as engineers, your system has diversity, and certain areas might not be operating at certain times. Whatever the case may be, you can overload the system, and overloading the system is actually better or preferable to underloading the system. Again, the refrigerant is going to be happier if you handle it this way rather than loading it. Some of the few projects we have that aren't working right are underloaded systems. So just keep that in mind. And then some manufacturers, again, I apologize, text is showing up quite horribly, but 200% would be the maximum allowable, like ever, combination ratio. But I personally do not recommend this. Other manufacturers, though, will recommend this, and that's why I want you to be aware that that number is out there, because some manufacturers say, yeah, go ahead, load it 200%. That seems a little risky to me, and LG does not allow that high of a connection ratio, but just be aware that that number is out there in case you come across it. So now, add heat recovery. I think that's everyone is most interested in, because this is where you really are able to start reclaiming some energy. So for that, we're going to add a heat recovery unit. Different manufacturers have different names for them. They call them mode selector boxes, and there's a few other names out there, but for this presentation, I'm going to call it heat or an HR box. And then that allows you independent mode control. That's how we get the simultaneous heating and cooling with this box. And basically, it controls the refrigerant state, and that's how it achieves this. And we'll talk about that a little bit more here. So one example of where you could use this is people exercising in gyms and cooking food are going to be hot and cooling. People laying in their rooms are just TV aren't doing any sort of physical activity, there's no hot stoves, they're probably going to want to be in heating or modulating their room to a little bit higher temperature. Or in an office situation where you have a bunch of people in a conference room generating heat and talking, and you have one guy in his office alone sitting by a window, they're going to have different requirements for what they want in their office. So you could simultaneously cool the conference room and heat the lone individual in the office by a window, or whatever the case may be. So we have two different types of heat recovery systems. We have two-pipe system, which is only used by Mitsubishi, just so you know. Everyone else is on the next type of system, but the two-pipe system works like shown in the diagram, and it has a liquid line and a mixed state line. And the mixed state line is what the HR box is going to use and fine-tune the conditioning of that mixed state line into the gas form that it needs, that is the right state for it to perform whatever action the controller is saying that that room or that box needs to be doing, so that the indoor units can get what they need. So then there's the three-pipe system, which every other manufacturer uses, and that has the same liquid line, but then it has a high-pressure vapor line and a low-pressure vapor line, and it's going to select what it needs and balance those so that using EEVs, and that's how it's going to get the proper conditioned refrigerant to the boxes so that they can condition how they need to be conditioning. And if you're interested, I do have a complex diagram of exactly how that works, which I can send to you if you're interested at all. So here are some piping strategies, and these are important because you want to minimize piping. So if you use a single port parallel approach, these red boxes are your HR boxes, and these would all be your indoor units. This is your outdoor unit. You can see that this reduces the amount of piping between the HR boxes and the indoor units, which we're abbreviating to IDU because we like to keep things short. It makes this run really long though, so you're going to have a lot of piping between your outdoor unit and the HR boxes, potentially, depending on where they're located. Then we have a multi-port option, which you can see is kind of the opposite strategy, where you reduce the length between your ODU and your HR box, but the other lengths can get kind of long depending on where you put everything. So there's kind of a happy medium on this one where you can do multi-port parallel, and you can add more of these in smaller quantities up here. Some manufacturers really do let you put like 20 units on one box though. LG doesn't have anything that large, but some of the other manufacturers really prefer this strategy where they put like 20 units on one box, and then you would do the same thing on a whole other individual unit. But if you do smaller ones like this and then continue off with another one, that's a really good way to kind of minimize your piping. And then there's another option, which would be multi-port series, which is kind of a cool option that allows you to minimize the length of everything by placing things where it needs to be, as close to the sections it needs to be in, if that makes sense. Like, you can take your HR box and place it in a room and route it to all of your indoor units such that those links are minimized, but then also place it in a convenient place so it's kind of midway between your outdoor unit, or however you feel, given the exact scenario, would best minimize your piping. Again, minimizing piping is what we're going for here, so just think, how can I do this the most efficiently when you're laying these out? And then this is what one of the boxes would look like. This is one of the ones where it pipes through like this, because you see the pipes on both sides. So, and then we're going to remember when we're doing our piping that you need Y branches and headers to split the refrigerant flow. Refrigerant isn't like chilled water, so you're going to need to make sure that you split it properly with engineered Ys and branch headers. That's how you're going to get your proper refrigerant flow. If you don't do this, again, your system is going to have issues, and we don't want that, so just start with the right materials and use your engineered Ys and branches for whatever manufacturer you're using. Don't mix manufacturers, because you don't know how different companies design things and how they size it. So keep that in mind as well, because again, less pipe, lower material cost, lower labor cost, and less chances of failure because you have less pipes and less connections everywhere. So keep that in mind when you're designing these systems. Also, another thing to keep in mind is obviously refrigerant safety. I'm pretty sure we've all seen these codes at some point or another. ASHRAE 34, which is just general ratings of refrigerant and the safety standards. And then ASHRAE 15 is the one about if you have a refrigerant leak and it all was hypothetically to leak into your smallest zone, then it has to be under a certain amount in order to maintain the safety standard. So again, just things to keep in mind when you're going from maybe a standard chilled water or air system that you're used to dealing with larger quantities of refrigerant, because these pipes are routed throughout the whole building. Like if it was in here, it would be routed over this whole ceiling if everything was not a air diffuser, if it was a indoor unit instead. So again, just something to keep in mind. And then the last note I have about this is that the compressor is basically the heart of this system. And that would make the piping, the veins or arteries. And we all know that when people have a heart attack, it's usually because there's a problem in their veins or arteries. It's not their physical heart as often. Or I don't know if I've actually heard of somebody who's had a heart reason why they've had a heart attack. But point being is that if you have a failure or you're continually dealing with compressor failures, it's most of the time, most often, due to problems with your refrigerant pipe installation. As engineers, pretty much the only thing you can do is lay it out as best you can, and that's kind of where that ends. But on the contractor side, if we have any contractors listening, this means be very careful with install the piping and how, like, as by the book as you possibly can. Keep those runs straight with the long sweeping bends and that sort of thing, not really jagged and wavy and all over the place. I've seen some interesting things out there, so everyone kind of does what they do when they get out in the field, but it really does matter. Okay, so on to the benefits of the system. We all know there's key requirements for HVAC systems. You want to be comfortable, you want to be efficient, and you don't want it to cost a lot. You know, happy medium. And I have to say, VRF does do these things. We can achieve all of these in comparison to a lot of other systems, actually. So they have low sound ratings. Even the outdoor units are only about as loud as, honestly, they're probably quieter than I'm talking right now to you. I've stood next to one and done training with it sitting right there and running, and everyone's talking no louder, quieter, honestly, than I'm talking to you now. I'm using my presentation voice, and if you're just using your indoor voice, you can still communicate with that sitting there. That said, I know you might not want to be sleeping with someone talking next to you. That level of sound, there are night setback modes you can use in order to make it quieter if you were to have it mounted outside the bedroom or in an area where for some reason make it quiet or anything else like that. And the indoor units are also quite silent, and they have a fan in them, so sometimes if the fan is on high, you can hear that a little bit. I have one in my office and it's not that loud. I can still work and not be distracted by it. And then in terms of cost, we have a breakdown for a building in Seattle. It was a multi-use project with 80 tons of cooling, and they did a comparison. Here's where VRF came in. Notice that VAV is actually a little more expensive, which would then get you that individual zone control, opposed to the RTU or split systems where you would have, if you were on the RTU, you'd have to give everybody whatever mode the RTU is currently in, that's what they're getting. So you actually come in midway and it's only, I think, what do we have here? Like 40,000 maybe? Is that what that is? Or even less. Anyways, you get a lot of cost savings with the benefits of being able to control your zones individually. So something to look at. And I know multiple manufacturers will run certain analysis for you. So if you don't want to check on how much savings you could be getting out of this system, the manufacturers are perfectly happy to help you out. So another thing is the size. I think we briefly touched on this. The size of the refrigerant piping is also, or is obviously smaller, but also the physical size of the cabinet. It's a smaller footprint and weighs less. So imagine that being on your roof opposed to one of these other systems over here. you're going to have potentially less structural requirements. You're not going to have to reinforce things as much, and you're just not going to take up as much space. Like looking at these pictures here, you have all this stuff going on this roof, and like that section right there, and like looks like some sections right there, and that is like a couple hundred tons of cooling sitting there on that roof, not actually taking up that much more space than all this ductwork or whatever is going on there. So it's kind of fun to compare. And then this is what it would look like, again, sitting on a roof. And again, that there is multiple tons of cooling just in that footprint. So good thing to consider. So benefits. Building owners, energy efficiency, therefore cost savings. Everybody wants to know they're saving energy and being good to the planet and saving money. It also reduces maintenance. These systems don't require that much maintenance. Once they're up and running, there's filters in the indoor units that need to be changed. And then other than that, it basically runs itself. Like it has an oil return cycle it does automatically on most of these things. So there's not a lot you got going on for people having to go out monthly or weekly or bi-yearly or however often. Like you don't really have to do that. Just vacuuming off the filters on your indoor units if you have the type that has filters. So not that bad. And then savings on the initial building cost, as we showed for various reasons earlier. And then increased leasable space. If you have these things outside and your refrigerant piping is really small, imagine how much more space you're actually using within the building. And of course, the owner is going to love that. So on to architects and engineers. Pleasing aesthetics. It's really small, more daylighting, and then reduced mechanical space. All those I feel like kind of go together, and they're reasons why architects can be really sold on this. Like, it's not gonna mar your beautiful design. They're gonna think, okay, that's great. I don't have this giant duct blocking this area that I wanted to put a bunch of windows. And that's also for engineers, it's relatively simple to design. Basically, all you need is loads, and then, like I said, you use your modular selections. Okay, this is how I'm gonna eat up my load with these various units. And then your manufacturer's rep can also help you out a lot with that. And then the controls are integrated. Again, like I mentioned, with the unit knowing how to run itself if you combine them on a combined chassis. Same thing goes for operation between indoor units. If you have HR boxes and the outdoor unit, you don't have to write any control sequences. Everything is knowledge, and it will do what it needs to operate itself as it should be operated. So for contractors, it's ideal for retrofits. Like we said, the pipes are really small. They're not going to have to go tearing out fancy crown molding in a historic building or something like that, and then getting blamed for ruining something, who knows. So great for contractors, also reduces their demolition. I've actually seen people run the refrigerant piping in abandoned ductwork to like keep it flat as like a hanger, or like cut the ductwork and then use it to hang this. Kind of creative, I thought. And then it's a lot faster to install because you're only installing the refrigerant piping, which takes time, but it's a lot less than installing 4 pipes for your chilled water system, every other piece of equipment that goes with that. Because the indoor units are basically a fan coil. So you're still doing those, you're just reducing your pipes. And then again, savings on controls for them. They might not have to hire a third-party controls contractor, at least for this part of the project, because, or if this is part of the project, they wouldn't have to hire one at all because the controls are already integrated. So when they put that unit up in the ceiling and they mount a thermostat, you're good to go. And then there's factory training available. So the factory will show them how to properly install these systems, how to commission them, how to start them up, all that important stuff in order to get this running and so that they know what to do, which is really important. Benefits for tenants. So again, individual zone control. Tenants, of course, love that. We all know. Everybody wants their own thermostat and to be able to do whatever they want in their individual zone. And then also this eliminates seasonal changeover. In my thing, we always have that awkward time. It's not quite ready for the boiler to come on yet, but they don't come quite, and you're like, well, now it's like a little bit cold, and then eventually they come and turn on the boiler, and you're like, oh, okay, good, we're good. So this, you won't have that. And then there's high turn down. So I know I said that the connection ratio or the load needs to be, basically we're going to shoot for 100, but that doesn't mean that once the units are connected, they all have to be running. You could have them all off be running on low, and the system will function perfectly fine. So that will be really good for the tenants, and like I said, in the heat pump scenario, where you don't have the individual zone control, but you have modulation, this will allow people to control what they need with the turn down, opposed to with the ability to do both modes at the same time. And then again, we said they're quiet, so tenants don't like to hear loud noises when they're working, sleeping, anything that involves them not wanting to hear something. So perfect. And then a couple quick design considerations for cold climates. One is enclosures. So you can do partial or full enclosures, and if you have your units sitting outside, even on a roof or whatever, you want to make sure that you get them away from the snow, which I should have put to mounting them a little higher so they're above the snow. You don't obviously want sitting in a snow pile, which I think everybody can assume for themselves. But one way to protect them from ambient winds, which can be cold and not beneficial, is putting them in a partial enclosure like this. And there are certain rules for that, but if you came to it, you'd be able to look at the manufacturer's recommendations and see where you need to point certain elbows or distances you need to maintain. And then another option would be actually mounting it inside and then ducting it to the outside. So you'd be getting rid of the majority of whatever hot or cold air is being expelled, and I think in certain cases you'd be able to condition that space then with just some louvers, but you also might have to add some supplementary heat. So again, 100% the most efficient thing you could ever be doing with these systems, but we do live in a cold climate, and considerations like this have to be taken into account so your system works when it needs to work. Though, like we said, it does, for the air source system, operate down to negative 22 degrees, and that's, again, in heating mode, not cooling mode. You don't want to cool people when it's that cold out, probably. And so we have that. And then it does, if on the next paragraph, you can operate in cooling mode down to low ambient conditions with the low ambient kit, so that also then brings the cooling down. Really need to focus on ambient kit, wind baffles, both allow you to take that cooling mode down to really cold temperatures, but you don't want to put this on a system where you're going to be heating, even for part of the year, because these systems are only for cooling mode. You basically just imagine that you put your heat pump in a box, and now your heat pump is taking all the cold that it can find inside, and now it's pumping it into this box. Where is it going to find any sort of heat in all that cold air? Nowhere. So you need to maintain high airflows and high levels of air changeover for these units. Therefore, you don't want a low ambient kit that slows your fan speed, and you don't want a wind baffle trapping that air in there and essentially making it a box. So something to keep in mind that I honestly didn't know until I started working in sales. So I thought that was kind of a cool thing to add, because it's not something that's really talked about that often. So yeah, that's all I have. Do you have any questions?
So is there any way to meter the costs for like individual units, like a condominium or a rented office situation?
Okay, so is there any way to meter the energy usage if you're in a tenant scenario or multi-unit scenario? Yes. I can only speak to LG for this one because I know my products, but we have a device called, I think it's a PCP. It's an acronym, but it stands for like Power Control Module, maybe it's a PCM or something like that, and it will actually monitor exactly what's being used by each tenant, and so you could actually use that data to bill them separately or just track it. So that's pretty cool. So does that answer your question? Okay. Anybody else? Okay.
What type of refrigerant is being used?
Okay, what type of refrigerant is being used? It's R410A. Sorry, I didn't actually mention that. I think it was just up there.
One of
Yeah, go for it.
Your slides showed that what's required, or are there other forms of piping?
So for this, what kind of piping is allowed to be used on these systems? I'm repeating them for the online audience. Yes, it does have to be copper that is meant for refrigeration piping. And in terms of fittings, the preferred method would be the brazed, full, proper fittings made by the contractor. Press fittings are, because of their potential to leak if they're not installed properly. There's just a higher chance of, I guess, installation error, but it is out there and is technically allowed even if it's not endorsed, but you still have to use the copper piping, though you can use either hard copper or soft copper. You think the outdoor part to the HR boxes would have to be hard copper, but once you get past that, then you'd be allowed to use soft copper to route to everything else. And then if you didn't have a heat recovery scenario, I believe the hard copper would have to go to your first Y branch, which would be inside. And then you could, again, you could split off and go to soft copper so that it's easier to route and you can just do those long sweeping bends opposed to having to put fittings on everything, and just makes things a little more complicated. So, any other questions?
Any examples around Anchorage of where these systems are installed, recent constructions?
Yeah, I actually have several going in right now. One of them is the Alpine Tower, or it's like Alpine. It's going in the C Tower. That's on Old Seward, and they have a heat recovery system. It seems to be going in really nicely. Let's see. I know there's some in the First National Bank facilities in various parts of Southeast, and then as well as the Kenai Peninsula area. And barring one that had a horrible installation, as I mentioned, those seem to be working well. Again, installation is super important. Install that as possible. Refrigerant doesn't like to flow through crazy dips and then you lose oil. It's not good. But yeah, there's quite a few. I can look through some too and send if you want a list. And those again are just LG. I don't know what other people are selling. So disclaimer.
Permitting problem like inside the city limits, or any examples of where the ground cooling is used?
So I don't have an example of that at the moment. I'm relatively new to this job and I'm not sure if my predecessor did any of those or not, so I don't have data on that one. I just know that it can be difficult to either have the resource available to you where you are, and also I have heard of issues with permitting, but again, I really can't speak to that because I haven't done one personally. Already have to put in like thermopiles, or a lot of times the civil will even be doing that on their part of the job. Their job is basically just to make the heat go away and keep the ground frozen. But if you work as a team and help them out and say, here, I have a system that can keep this ground frozen for you, which is what you're trying to do anyways, and you can recover that heat, then that's a plus for the job. And then you're not worried usually about, that's not as much within the city limits, it's more the more rural projects. There was a library, they did a system like that. They used the water source heat pumps to do that, I believe, which was pretty cool.
Okay, so let's thank Elena for the wonderful presentation.
Thank you. Oh, and the password is refrigerant, all in lowercase, for those of you listening at home or from your office. Awesome. Yay.